Well, we've spent a lot of time thinking about statements, and in particular, thinking about conditional statements. Now we're ready to start solving problems and writing proofs. Before that, I want to discuss a couple questions about what mathematics is and what proof is, so that we know what we're talking about when we talk about solving a mathematics problem and proving a mathematical statement. Then we're going to figure out how we actually operationally go about proving conditional statements. And then we're going to prove a theorem first informally using an outline, and then we're going to convert this to a formal proof, and we'll show you some of the principles that we're going to use in doing that. So first of all, I want to talk a little bit about math, about what it is and what its nature is, and I'm asking a question that may seem somewhat innocent, maybe not so. What is mathematics? And on the face of it, it seems pretty obvious. You've been doing mathematics for a long time, ever since you were little. And so you may think, well, that's an easy question to answer. But if you get thinking too deeply about it, I mean, where exactly do we draw the boundaries between what is mathematics and what is not mathematics? And there are lots of ways you can answer this question, lots of good ways, all right? So I'm going to answer it in what I think is a good way, not the good way. There are lots of others that are just as good. But my answer is, well, it's what mathematicians do. Now, at first that may seem like just a real smart aleck thing to say, and I'm just trying to be funny. And I'll be honest, that's a little bit true. I'm a little bit trying to be funny. However, that statement, it is what mathematicians do, is actually important in how we think about mathematics. So if I sort of focus on the mathematicians part of that, it sort of tells us that this doesn't come from nowhere. I mean, mathematics just doesn't come from the air. It doesn't come from anything but a community of mathematicians that decides collectively what is mathematics and what is not mathematics. It's really mathematicians that decide what is mathematics and what is not mathematics, unless it's something that is sort of mathematicians want to be mathematics and maybe somebody else wants it to be part of their field. That's a little bit different. There has to be some negotiation there. But basically, it is decided by a community of mathematicians. And then if I concentrate on the do part of that statement, it allows us to focus on the actions of mathematicians. What do mathematicians do? And well, that's my next question. What do mathematicians do? And broadly speaking, there are basically 4 different things that we do. And they're not things that just mathematicians do, but these are the important things that mathematicians do. So first of all, we ask a lot of questions about math. And usually the way we present those questions is as problems. We make up problems. If a mathematician does not have a problem to work on, then we're not being mathematicians, or at least we're not being research mathematicians, right? So, first thing we have to do is we need problems, or otherwise there's nothing for us to do. Then, of course, once we've asked questions, the natural thing to do is to try to answer them. And so if I'm thinking of that in terms of problems, if I make up a problem, I'm going to try to solve it. I'm going to solve that problem. Now, once I solve that problem, I may be perfectly happy, yay, I solved that problem, but if I want to share that with my community of mathematicians, I'm going to have to do 2 things, right? I'm going to have to explain what my solution is, and the other, perhaps even more important part is I'm going to have to convince other mathematicians that my solution is correct. And that's where we start talking about proofs. The proof is just convincing something that convinces mathematicians that your solution to a mathematical problem is correct. Now, there is a 4th thing that a lot of mathematicians do, especially if they're experts in their field. They may notice some connections between different parts of mathematics and be able to bring them together and unify them into a concept. And this process you could think of as being called abstraction. And that's something else that's really important. We might do a little bit of that in here informally, but this isn't something that we're going to focus on. Mainly in our class, we're going to focus on getting problems, solving those problems, and writing the proofs. So we're going to concentrate on writing theorems and then proving them. Okay, so now that we know that proof is a central part of mathematics, now we got to ask the question. Yeah, we got too many questions there. What is proof? Well, what a proof is, it is a rigorous explanation of why something, and by something I mean a statement, a mathematical statement, why that something is true. Now, rigorous is kind of a sticky little word there, but what I really mean by that is rigorous is an argument that has no holes in it. So nobody's going to be able to come in and poke holes in your argument. Your argument is airtight about why this something is true. And being able to determine when an argument is rigorous, a proof is rigorous, well, a helpful thing, as you may not be surprised about, is I use a model. And my model is, I call my model Peeves. You can name your model, this particular model, whatever you want. I like calling this one Peeves. And who Peeves is, so who is Peeves? You got to think of Peeves as someone who makes it as difficult as possible for you to prove something. And not as difficult as possible, like you're trying to prove it and then Peeves like throws something at you. No, it makes it as difficult as possible for you to think that you're finished writing your proof. So always looking at what are the things you left out. What are the mistakes that you made? What are the holes in your argument that you haven't considered yet? So, and when Peeves does this, Peeves is not bound by much. Peeves is bound by the rules of logic. So Peeves can't just say you're wrong and and then sticks his tongue out at you, right? But so Peeves is bound by the rules of logic, but otherwise can be as disruptive and annoying as possible. Peeves looks for mistakes or bugs in your proof. All right, so now that we sort of have a way of thinking about, okay, now how do I know I have a rigorous proof involved here? Let's actually start talking about practical ways of proving actual statements. So how would you prove a conditional statement of the form if P, then Q? So P, if one statement, then another statement. Well, we already know, where P and Q are statements, of course. Well, we already know when the statement is true and false. It is false when P is true and Q is false, and it is true otherwise, right? That's what we learned in the last video. So let's think about how we'd go about this. Well, I mean, there are a couple possibilities for P, right? Either P is true or it's false. Now, when P is false, the statement is automatically true. If P is false and Q is false, the statement is true. If P is false and Q is true, the statement is also true. So whenever P is false, the statement is automatically true. There's really nothing to prove, which means that we can ignore this case. Now, I do want to point out, we're not ignoring this case because the case where P is false is not important. We're ignoring this case because when P is false, the statement is automatically true, so there's literally nothing to prove. If there's nothing to prove, there's no reason to even consider it because it's already automatically true. We only need to prove the things that at this point in our lives may or may not be true as far as we know. Which means that we only have to look at the case that P is true, which means that we can assume that P is true. So that's great. So we start our conditional statement by assuming that P is true. Now, when P is true, we have two possibilities again. Either our statement Q is false, in which case if P then Q is also false, or when Q is true, in which case if P then Q is true. So that means when we prove the conditional statement, we get to assume P is true, because when P is false, it's automatically true. And since we want to eliminate the possibility that Q is false, because that would make our conditional statement false, we need to show that Q is true. So we assume that the if part is true, P, and then we show that the then part is true, that's Q. All right, so now let's actually try to prove a particular theorem. And in order to prove a theorem, you actually have to have something to prove the theorem about. You need to have some actual math. And with that, you usually need to start with some definitions. So we're going to talk about even numbers and odd numbers, and first of all, define them precisely, and then use those definitions to prove something about even numbers and odd numbers. So an integer is even if, well, let's see, how does an even number work? Well, it's going to be some number that is 2 times another integer. So you have it's an integer, first of all, and secondly, it is 2 times another integer. And a way of writing that in a more computationally friendly way is n is even precisely when n is equal to 2k, where k is some integer. Now an odd number, there are a couple ways that you can define an odd number, but I'm going to define it as it's a number, it's an integer that comes right after an even number. So an integer odd if it comes after an even number, and again, if you want a computationally more friendly way of saying that, in other words, n is odd precisely when n is equal to 2k plus 1 for some integer k. So 2k is the number that comes right before n, you add 1, you get to the next one after that even number. That's your odd number. Okay? So now the question is, we're asking a question just like a good mathematician should. What can you say about numbers that come right after odd numbers? In other words, our problem is if we have an odd number, what can we say about the number that comes right after it? Well, you probably don't have to think about that too much, but if you looked at some examples or maybe considered it conceptually, you'd probably figure out, oh yeah, if n is an odd integer, right after that, it's going to be an even integer. So here's our theorem. If n is an odd integer, then n plus 1 is an even integer. And we're pretty confident that that is true, but we still have to prove it. Okay, so before writing a proof about this, let's first of all work out informally why it's true. Let's show our scratch work, figure out an outline of the proof before we actually write a formal version. So we're going to assume the if part, n is an odd number, and then we're going to show the then part, that n plus 1 is an even number. So we assume n is odd, we prove n is even. Which means that we're starting with n being odd, that's what we're assuming. And what odd means is that n is equal to 2k plus 1 for some integer k. And we want to show, and this is where the end of the proof is going to be, that n plus 1 equals 2 times, well, we can't exactly say 2 times k. In fact, it's not going to be 2 times k. But we do want it to be 2 times some integer, right? That's what an even number means. An even number means 2 times an integer. Not necessarily k, though. So that whatever goes in that parentheses is going to be an integer, but it's not necessarily k, and I'll even give it away now. It's definitely not going to be k. But we'll see what it is in a bit. We'll have to work with this. So let's see. So I want to show that n plus 1 is an even number, so let's take a closer look at n plus 1. Well, we know that n is equal to 2k plus 1, right? That's our assumption that we're starting with, right? And so if we substitute n equals 2k plus 1, that's what we get. If we simplify that, combine those ones, we get 2k plus 2. And now an interesting thing happens. We have 2 in front of the k, and we have a factor of 2 with the plus 2. If we factor out that 2, we end up with 2 times the quantity k plus 1. And lucky us, that's exactly what we want to end up with, right? N plus 1 equals 2 times something, where that something is an integer. Oh wait, but we first have to figure out, is that k plus 1 an integer? Because we don't exactly know what k is, and so k plus 1, we don't know exactly which integer it is. How do we tell whether it's an integer or not? Well, it turns out, remember, we don't know what k is, but we do know that k is an integer. We also know that 1 is an integer. But so because k and 1 are integers, we know that k plus 1 is an integer. And let's see, why is that again? Yes, closure, right? The integers are closed under addition, which means that when you add 2 integers together, that always gives you another integer. So k is an integer, 1 is an integer. That means k plus 1 is an integer. So it looks like we have our proof. All right, well, but let's organize this into an outline just to make sure it works out. So we start off, we're assuming n is odd, which means that n is equal to 2k plus 1, where k is an integer. We do n plus 1 by taking that equation, adding 1 to both sides. We end up with 2k plus 2, and then we factor out the 2. Then we make the argument that k plus 1 is an integer, since the integers are closed under addition, and since k and 1 are both integers themselves. And again, closed under addition just means if we add 2 integers together, any 2 integers, that gives us another integer. So that's what's happening with that k plus 1. And since n plus 1 equals 2k plus 1, and since k plus 1 we just showed is an integer, that means that n plus 1 is an even number. And that's the end of our proof. All right, so this is an outline of our proof. It's not the actual proof, right? Because we gotta write this in a nice way for our reader. Remember, our goal is to convince other mathematicians it's true, and if we write a crappy proof, they're not going to be convinced. So this is an outline of our proof. Our actual proof is going to be the same logic. The only thing is we have a couple rules that we have to obey when we write this. First of all, our proof needs to be logically sound. And that's actually not going to be bad. We put this through the ringer. I think Peeves is going to be okay with this one, right? Make it so Peeves can't criticize it. Peeves is pretty much going to have to go along with the logic that we have there. But the second thing, and this is almost as important, I was going to say it's more important or as important. I'll say it's almost as important, is you want to be nice to your reader. If you want to convince your reader that your solution is correct, writing an incoherent, even if it's logically sound proof, is not going to put them in a good mood to agree with you. right? So we want to be nice to our reader by writing this in a clear and pleasant way, right? Make sure your reader understands what you're assuming, what you're going to show, all your logical deductions, and just generally, lead them through the proof so that they don't get confused and that they're happy with you. All right, so here's our theorem, where if n is an odd integer, then n plus 1 is an even integer. So the first thing that we're going to do to be nice to our reader is we're going to tell the reader what we're assuming and what we're going to show, right? We assume that n is an odd integer, and we prove that n plus 1 is an even integer, right? So the reader knows exactly what the structure of our proof is going to look like. So that means when we go to the next thing, since n is odd, they're not going to say, why are they assuming n is odd? The reason why is, we just told you in the previous sentence. So since n is odd, we can write n equals 2k plus 1, where k is an integer. We're just using there the definition of odd number. By adding 1 to both sides of the equation, that's kind of a nice thing to do for your reader, letting them know how you get from one step to the next. We're going to take that equation we had, we're going to add 1 to both sides. That's logic that your reader is going to be happy with. You get n plus 1 is equal to 2k plus 2. Now remember, the next thing we did was factor out that 2, but really what we're doing is we're using the distributive property. So by the distributive property, we're giving a nice justification for our next conclusion. We have 2k plus 2 is equal to 2 times the quantity k plus 1. And so putting that together with what we had previously, that means n plus 1 is equal to 2 times the quantity k plus 1. Right? Again, leading our reader through our logic. Recall that k is an integer, right? We're gonna help our reader understand our closure argument. Since the integers are closed under addition, we have that k plus 1 is an integer, right? So we're reminding that our reader that k is an integer, and so that means that k plus 1 is an integer as well. And since we have n plus 1 is equal to 2 times the quantity k plus 1, it follows that n plus 1 is twice an integer, and thus n plus 1 is even. And now we put something that is actually really important, which completes the proof. We're reminding our reader that we're at the end of the proof. We just showed what we wanted to show, that n plus 1 is even, and so the proof is over. All right, so now that you've kind of seen the process of trying to prove a theorem, I think you're ready for the proofs of our statements in Introduction to Proofs, and that's on the PDF file included with this video.